So let's talk about how you actually get the estimates, or how R or whatever figures these things out. And I'm going to go through a derivation, and again, if this is not your thing, then feel free to skip over this part of the lecture. Remember, if you have regression to the origin, you want a line that's forced to the origin that has no intercept. So you have a single predictor x and a single predictor y, and you want no intercept. The slope estimate was just this sum of the product x times y divided by the sum of the x's squared. We talked about that earlier on in the class. Now let's see if we can use that result to derive the least squares estimate when we have two regressors, and then I think if you've got the gist of this, you could see how it would work for 3 and how it would work for 4 and so on. Okay, so derive is maybe a bit of an ambitious term as to what I intend to do here. What I guess I mean is develop, and I'm going to ask for those that are interested to fill in the details on their own, but what I'm going to do is simply develop the estimator a little bit. And the reason I'm going to go through this development is I think it illustrates what multivariable regression is doing. If you're not too interested in this sort of development, then I think you could reasonably skip over this slide or this set of notes and not worry about it. But if you're interested and you kind of want to understand how multivariable regression works, I'm going to give a development that's more intuitive than what you would get with something like linear algebra. In addition, I have some videos on YouTube where I go through the linear algebra development if you'd like to watch those. But I don't think that that's actually necessary to sort of understand what's going on. So let's consider two regressors. We have summation of the outcome, yi, minus the first regressor, xi1 times beta1, minus the second regressor, xi2, x2i times beta2 squared. That's the least squares criteria that we would like to minimize. So for example, x1i might just be an intercept, and x2i might be some, is a covariate of interest, blood pressure or something like that. Okay, so here's the trick. Imagine if I were to just know beta 1 or fix beta 1. Then I get yi tilde, let's say, is equal to yi minus x1i times beta 1. And then this equation becomes summation yi tilde minus x2i beta 2 squared. Well, then this is exactly regression through the origin with just the single regressor x2i, but the outcome y tilde I. So we know what the estimate for beta 2 would have to be. It would have to be summation yi tilde x2i over summation x2i squared. Now, what you can do, this, and remember yi tilde, remember its definition over here. If we were to plug it in, that's a function of beta 1. So what I could do is, now that I know that my beta 2 has to satisfy this equation, I can take this and plug it back in here, right? Or equivalently back in here. And then what that yields is an equation that only involves beta 1 and a regression through the origin for beta 1. And if you want to, you can fill in the rest of the details. What it works out to be, and this is the interesting part, is that the regression slope for beta 1 is exactly what you would obtain if you took the residual of x2 out of x1 and x2 out of y, and then just did regression through the origin. So kind of what multivariable regression is doing is it's the coefficient for x1, say beta 1, is the coefficient having removed x2, the other covariate, from both the response and that first predictor, x1. Similarly, the regression coefficient for x2, beta 2, is going to be what you get if you were to remove x1 out of both the response y and out of the second predictor, x2. We're going to go over this point a lot, and I know it's probably confusing to begin with, but it explains what multivariable regression is doing. A coefficient from a multivariable regression is the coefficient where all the other variables have been their linear effect on that predictor and the response has been removed. And this is a very useful fact, and we'll exploit it in a variety of ways. So in case you skipped over that previous slide, I wanted to go through the result because it's important for your understanding of multivariable regression. So remember, we have two covariates in this case, an x1 and an x2, and of course one outcome, y. And we're interested in a model that has only the two covariates and a regression slope beta 1 for the first one and a regression slope beta 2 for the second. The result is that the fitted coefficient for beta 1 is what you would get with regression through the origin if I had removed the second coefficient, x2, if I had removed its linear effect from both the response y and the first regression variable, x1. So that's the sense in which multivariable regression, the sense in which the coefficient for x1 has been adjusted for the effect of x2, because the linear effect of x2 has been removed from both the response y and the first predictor x1. Similarly, the same thing could be said about the coefficient for x2, beta 2. Once we get its estimate, beta 2 hat, it is what you would get if you were to remove the linear effect of x1 out of both the response y and the second predictor x2. And this is why multivariable regression relationships are sort of thought of as having been adjusted for all the other variables. We'll go on in the next slide and talk about how this relates to a full multivariable regression where you have lots of predictors. So let's go through the case that we already know of simple linear regression, where one of our covariates is an intercept term and the other one is some covariate of interest. So here we have yi equals beta 1 x1i plus beta 2 x2i, where in this case I'm just going to assume the second one is the intercept term, whereas we usually assume that the first one is the intercept term, but that of course doesn't matter. So if we adhere to my rule that the the estimated beta 1 coefficient is going to be the one that's obtained by getting rid of x2 out of the both y term and the x1 term, let's think about what we would get if we fitted x2 on y. Well, x2 is just an intercept, so as we know in intercept-only regression, the fitted value is just y bar. And so the residuals are just the observations yi minus y bar. In other words, the centered version of the y's. And then if we were to fit x2 on x1, again, x2 is just a constant. If we were to do the fitted values, the coefficient would just be x1 bar, the mean of that covariate. And so the residuals would just be x1i minus x bar, the centered version of that covariate. So getting rid of this intercept term from the y is just centering that variable, and getting rid of this intercept term from x1 is just centering that covariate. And then my fitted regression estimate is given down here is just the product of the centered y's times the centered x's added up divided by the sum of the centered x's squared. I give you that formula here and you can work with it, and it just works out to be the standard regression slope, the correlation between the x's and the y's times the ratio of the standard deviations. So now let's extend this to more than two variables so that we can start dipping into the idea of multivariable regression. So hopefully you see where we're going with multivariable regression. Our least squares criteria is now the distance between our observed outcome, yi, and x1 times its coefficient, all the way up to xp times its coefficient, the squared distances between those. If we only have two regressors, an intercept and a slope, this amounts to minimizing the sum of the squared vertical distances between the outcome y's and the predictors and the prediction on the line. If it's three regressors, an intercept and two regression variables, then the fitted line is, or the fitted construct is no longer a line, it's a plane, and the least squares criteria is minimizing the sum of the squared vertical distances between the outcomes and the plane. If we take more than three variables, an intercept, and then let's say three covariates, then we can't visualize it anymore. So, but it's sort of the generalized idea of the distance, the vertical distance between the y's, and some generalized version of a plane. And what we've seen is the idea that multivariable regression adjust for the other variables in a sense by taking residuals. So for example, if we take this coefficient in front of x1, beta 1, the way in which we interpret beta 1 is that the remaining regression variables, x2 up to xp, have been linearly removed from both y and x1, and then the relationship between those residuals investigated by themselves. So in a sense, y has been adjusted for the remaining variables, x1 has been adjusted for the remaining variables, and we look at those two together so that beta 1 can be thought of as an adjusted effect, having adjusted for the linear relationship with the other variables. So what we're going to do now is go through some computer experiments to illustrate that this is how LM works. And then in the next lecture, we're going to go through some examples in how we interpret the coefficients in a context.